Well, in this section 4 we talk about model sets and model structures, so parameterized structures that can represent the actual set. But before we talk about model sets and model structures, remember that this is the data generating mechanism. Remember that we have a deterministic part and a stochastic part, right? The deterministic part is described by the input-output transfer function g of q, well, that you can also write as follows, and this is then the associated impulse response. The stochastic part can be seen as E of t, which is white noise. It's a sequence of variables that are independent, identically distributing according to a Gaussian distribution of zero mean and variance sigma square. Well, this white noise goes through a noise filter, h of q, and that can also be described as follows using its associated impulse response, and h of q is monic, so the first element of the impulse response is 1. So the question is, if we have data coming from this system, okay, and we'll call this data Zn, and it's a set of output data. Let's say that we have n output data and we have n input data. So based on such a set, is it possible to obtain a representation of the system? Well, you can see here that when you look at this, well, there is an infinite amount of information, right? This is the impulse response of the system and of the input-output transfer function, and this is the impulse response of the noise model. So in here, in this sum, well, there are an infinite amount of g of k and an infinite amount of h of k. So working with the impulse responses is not a good idea. So what we'll do is use a parameterized structure. So we'll use a parameterized transfer function where, well, the transfer function is parameterized by a vector theta, right? And we'll do something similar for the noise model. And in theta, well, you have all the parameters that are associated to this model structure. So these are the particular model structures that I've discussed in the previous slide, and how you parameterize such a model will depends on the structure that you use, and we'll see in the slides that will follow that there will be different ways of representing g of q theta and h of q theta. This will lead, for instance, to ARX models, output error models, ARMAX models, and so on, right? So once you have chosen a parameterized model structure, then you can have a look at the associated model set. Well, the model set is all the models that have this particular structure where theta is living in some set. Well, for our purposes, we can say that theta is in Rd, so there are d parameters, but what this means is that, for instance, you could impose additional restrictions on the parameter theta. So you could say, for instance, that one theta is positive or the other one negative, or it could be living in a certain interval. For our purposes, we'll simply say that theta is in Rd and that there are d parameters. So what will be the idea in the, well, coming slides? Well, once you have a data set z of n, and I've explained what this data is, well, it's n input data and n output data, you can use your model structure to construct a prediction of y at time t given your model. Okay, for every parameter theta, there will be an associated predictor, right? So the idea is now to select a model, and to select a model we need an estimate of theta, and this will be, well, dependent on the number of data that you have, and this parameter will be obtained by minimizing over theta, well, some cost. Okay, and we'll write it like this. It will of course depend on theta, and it will depend on the data set, right? And you can imagine that this cost looks like something that will look at the difference between, well, the measurements and the predicted output, and what we'll very often use is simply the sum of the residuals squared. Okay, so y minus y hat t theta squared. This will be the cost, right? So in this way we'll obtain an estimate of theta and we'll obtain an associated model. Just as an additional remark, I've said that we'll consider several model structures. I've spoken about ARX, output error, and so on. But even when you have selected the model structure, let us say we'll choose an ARX model structure, you have an additional design parameter, which is the choice of the number of parameters in your ARX model structure. So D here will actually also, the size of the parameter vector will also be a design choice. So here's an illustrative example. We parameterize the system as follows. Well, we say that the noise model is very simple because here HQ of theta is simply 1, and this is the parameterization of the input-output relation, and, well, the numerator is fixed and there is one parameter in the denominator polynomial. The variance of the noise is unknown, so it's also a parameter that needs to be estimated. So once we have parameterized the model, we can consider the model set. So it's the parameterized structure where theta lives in some parameter set. So this parameter set here is theta is equal to theta 1, theta 2, and in this case we have put some restrictions on theta. So its modulus of theta 1 needs to be smaller than 1, and theta 2, for instance, lives in this interval over here. So in the examples that we'll cover in the system identification lab, this is not something that you have to worry about. This is something that is done automatically in the system identification toolbox. So we'll start our library of transfer function models with equation error models, and those models are often called ARX models, and we'll see why next. So why equation error models? Well, the relation that the input outputs follow is the following one, and you can see here that if you take the difference of this one and this one, well, you have white noise, so hence the name equation error models. In here, A is a monic polynomial and you have NA parameters, right? And B is a polynomial with NB parameters, and these parameters are stacked in the parameter vector theta. So if you divide by A, you can see here that the input-output transfer function is the B polynomial over the A polynomial, and the noise model is 1 over the A polynomial. You see that G and H have the A polynomial in common. So what you see here is the ARX model when nk is equal to 1, and nk here really is the delay in the system. In general, we'll have a delay that will be different from 1, and we'll use a b polynomial that will look like this, right? The number of parameters will still be nb, but then nk is the delay that you can select. And when you'll run the ARX command, what you'll do is choose NA, NB, and the delay NK. ARX models or equation error models obey the equation AQ y of t is equal to BQ u of t plus e of t. So e of t enters as a direct error in the difference equation. Indeed, it's e of t is the difference between what we call the autoregressive part. So autoregressive means that y is constructed from previous versions of y, past versions of y, and so e of t is the difference between the autoregressive part and the exogenous input. So that's the part that comes from the input signal. So hence the name ARX. The A comes from auto, the R from regressive, and the X from exogenous. And so we take the X over here. So let us divide by A and the A polynomial, and then we obtain the deterministic part. So this is the input output transfer function, and the stochastic part, 1 over AQ E of t, and this is V of t here. This is the noise model, and this is V of t. If you have n is equal to 0, then really AQ is equal to 1, and the model simplifies to simply y is BQ u of t plus e of t. So we'll assume here that nk is equal to 1 for simplicity, and then we can write y of t as, well, b1 u of t minus 1 plus lots of terms up to b and b u of t minus nb plus e of t. And this we can rewrite as follows. So we'll use the index L that ranges from 1 to nb. So we'll call these ones BL, and then we have to put u of t minus L, and then of course plus e of t. You can see here, because this plays the role of the impulse response, well, that in the impulse response that you have only NB terms. Okay, in the impulse response the element NB plus 1 will be 0, as will be all the other elements further in the impulse response. So if you have NA is equal to 0, we have just shown that, well, this corresponds to a finite impulse response. Okay, so a finite impulse response model is an ARX model where NA is equal to 0. As soon as you take NA different from 0, then you have an infinite impulse response model. So let us now have a look at the one step ahead predictor for this ARX model. So here, as a reminder, we have the one step ahead predictor for a system that is described by a input-output transfer function g of q and a system that has a model h of q. So we have to write this one step ahead predictor, but we have to work with g q of theta and h q of theta. So this is why we write it like this. This is the predictor of y at time t. Given information up to time t minus 1, we'll drop the t minus 1, otherwise the notations become too heavy, and here I have put it in. But of course this prediction depends on theta, right? So remember that gq of theta is bq over aq, and that hq of theta is 1 over aq, right? So we'll have 1 over hq theta times gq theta, and we'll be left with the b polynomial over here. And here we have to take the inverse of the noise model, so we'll have 1 minus aq acting on y, right? And this you, well, maybe first write a of q here. A of q is a monic polynomial, so it's 1 plus a1 yt minus 1 and so on. So you can see here that the ones will disappear. So assume a general delay nk. We'll have b1 here, u of t minus nk, up to b and b, u of t minus nb minus nk plus 1. Okay, and then we have to add the terms that are coming from the a polynomial times y, so minus a1 yt minus 1 up to minus ana y of t minus na, right? So this is the expression of the predictor. And so what we'll do to ease notations is use what is called the regression vector. And this regression vector, it's a column vector, as you can see, because there is a transpose over here. It's constructed from past outputs, okay, and past inputs, okay, and this is the regression vector in the general case where nk is general. So we had already defined the parameter vector, which is also a column vector, so both are column vectors. And well, this expression here, you have had a course on linear algebra, you can rewrite it as the scalar product of this vector times this vector. So you can write it like this, or you can write it like this. So we have just seen that it's very easy to write the predictor for an ARX model. We have seen that, well, the prediction can be written as follows, and you can see that the prediction is linear in the parameters. And what is very important is that this, well, if we take this expression here, theta here is a column vector, this one here is a row vector. Well, in this phi transpose of t, in this regression vector, there is no dependence of theta. And this means that, well, you can easily obtain an estimate of theta using least square methods, and this should ring a bell. This is something that you have seen in, well, last year's course of linear algebra and applications. So let us have a look at that in more details. So this is the prediction at time t using the parameter vector theta. Well, this should correspond to y of t, the measurement on the actual system at that same time. Okay, so what we can do is write a system of equation, assume that we are given a data set with n data points. So what we can do is write a system of equations as follows. So y1 here can be written as, well, we'll take the expression over here, but we have to evaluate it in 1, phi transposed in 1, right? This is a row vector, and then we have to multiply by theta, right, which is a column vector. And what we have done for y1 we can do for y2. We have phi transpose 2 over here, again times theta, and we can do this up to yn phi transpose of n. Okay, so this is the regression matrix. Okay, to make things simple, I will write this system of equation as y is phi times theta, and phi is a matrix that is in R n, that's the number of data that I have, times d, and d is the number of parameters that you have here in theta. In this case, d is equal to na plus nb, right? So this system of equation has lots of rows and, well, fewer columns. Okay, so this is typically a least squares problem. Okay, last year we had seen the least squares problem, but we had different notation. So we had ax is equal to b, and we had seen that x least squares is a transpose a inverse a transpose b. So here theta hat based on n data will be, well, phi transpose phi inverse times phi transpose times y. Okay, so this is quite easy to obtain. You do not need any optimization, and there is no risk that you end up in a local minimum. You will always end up in the global minimum. So previously we had seen that the one step ahead prediction is really bq u of t plus 1 minus a q y of t, right? So what you see here on top, this part over here, you obtain it over here. So this is bq u of t. It's constructed from past values of the inputs, right? And when you have them, well, you have to do some multiplications and then addition, right? And this is really the case, the general case, where the delay can be anything. So what you have over here, remember that this one over here is really minus a1 q minus 1 minus a2 q minus 2 up to minus a q minus na. So this part over here, you'll find it here. So this is really, well, with the, so this is rather this part over here acting on y of t. Okay, so this part you find over here. So this is how you can visualize the ARX predictor. So in this linear system identification course, The one step ahead prediction is obtained from, well, linear combinations of delayed versions of the inputs and delayed versions of the output. Well, as you know, there is an associated course that, well, tackles non-linearities, and you will see that what you could do is take these delayed inputs and delayed outputs and use them as inputs to a non-linear system to produce a one-step ahead prediction. So what you could do is replace what is inside the box with a neural network, for instance, and this is what is shown in the next slide. So this slide combines IDs that is coming from this part of the course with IDs that are associated with the second part of the course given by my colleague Thomas Muser. Well, instead of using a neural network as shown previously, what you could do is, for instance, use a neural network and only use the delayed inputs and use a neural network to replace this linear construction of this exogenous input and leave the autoregressive as linear. Okay, this would also be an alternative, and this would model kind of an input nonlinearity. You have probably guessed that what you could do is leave the input side, okay, so the exogenous input side linear, and then use a nonlinearity in the autoregressive part. So this would amount at putting a neural net over here. And yet another alternative would be to, well, use a neural network at the input side. Okay, so let's call it neural network 1, and use another one over here, right? Neural network 2, but you still have a separation between, well, the exogenous input and the autoregressive part. So the four options of the non-linear ARX predictor can be used to obtain a non-linear prediction or non-linear predictor, but you would have to implement this yourself in Matlab Simulink. There is also the option of using a non-linear ARX predictor in Matlab, but it's constructed a bit differently as shown in the previous slide. The estimator is really taking the regresses in the same way that I have shown before, but it's using a linear function. So this will actually be an ARX model, and it's adding a non-linear part on top of that. So the advantage is that here, well, you can initialize the model using a ARX model that you have identified up front. So here are the commands that you can use in Matlab. The first part we have seen before, right? So when you do your work in the system identification lab, please use an object. It makes things simpler. So here is the Matlab command. It's using the data over here, and this is NA, this is NB, and this is NK. So This model comes in a certain format, and if you type present this model, you will see all the parameters with their associated confidence interval. So this is the linear ARX, and as said, you can also use the NLARX command to identify a non-linear ARX. The type of non-linearity will be explored in the course of my colleague Thomas Museur, but also have a look at the help associated with NLARX. Obviously, the ARX model is computed from a least squares problem. So you have a least squares solution, so you have the global minimum. When you'll have to identify a non-linear ARX model, you'll have to do optimization, and you run the problem of going to a local minimum. So the problem of initializing things is very important. So with this NLARX command, what you can do is, well, initialize the model at the linear ARX model, and then again you can use the command present to have a look at all the parameters in the model. Okay, so this problem of ending up in a local minimum is crucial. So what you can do is maybe reinitialize the initial estimate, and you can do this using the command init, and then run the NLARX command from this new initial values of the parameters and see if you have much difference. You can do this several times to, well, see if it changes a lot and to avoid being trapped in a local minimum. It goes without saying that before trying a nonlinear ARX model structure, you should always first identify an ARX model structure and then see if a nonlinear ARX model structure brings a substantial improvement. If it does not bring a substantial improvement, keep the ARX model, because it is really much simpler from a computational point of view and from an implementation point of view. For instance, if you have to implement your linear predictor on a PLC, this will be of course much simpler than implementing a non-linear predictor. So we have seen the ARX model, and well, the major disadvantage of the ARX model is the lack of freedom in describing the disturbance model. Okay, the disturbance model h of q is 1 over a q for the ARX model, and well, remember that a is also used in the input-output transfer function g of q. So the idea here is that, well, instead of having a 1 here and adding just white noise, we could say, well, I'm going to add white noise going through this filter over here. And this filter, if you look at it, this term, this is really, because c is given over here, this is e of t plus c1 e of t minus 1 up to c and c e of t minus nc, right? And this is what is called a moving average of e of t, hence the name ARMAX model. AR comes from the autoregressive part, remember, the X comes from this exogenous part, and now you have a moving average on the white noise. Okay, so the advantage will be to have additional freedom in describing the disturbance model, but we'll see later that there is also a major disadvantage that we'll tackle later. So what you can do now is extend the parameter vector. So this is a column vector, right? So here below you stack the parameters C1 to C and C. And as you can see here, well, my input-output dynamics have not changed with respect to the ARX model, but I have indeed some extra freedom in the noise model. So with the ARMAX model, this is the input-output transfer function, right? The same as for the ARX model. And here we have the noise model, and it's here that we have additional freedom. You will sometimes encounter what is called an ARMAX model, and here y of t is replaced by delta y of t. So this is y of t minus y of t minus 1. So you can write it as y of t times 1 minus q minus 1. And you can see that this is, well, forcing an integrator in the system. So you'll have a factor 1 minus q minus 1 into the polynomial a of q, and I said integrator, so this explains the e that is appearing over here. And this is something, well, you have used a model that is close to that in the course of model predictive control of my colleague Thomas Museur. So we can do the same exercise as we did for the ARX model and write the one step ahead predictor for the ARMAX model. So remember that the one step ahead predictor, if you know the input-output transfer function g and the noise model h of q, is given by this expression over here. So here we work with the ARMAX model, so we have to work with g of q theta, which is bq over aq, and we have to work with the parametrized model, noise model, which is cq over aq. So very easily, this one inverse times this one will produce you bq over cq, and here we have to use 1 minus the inverse of this one. So this is the one step ahead predictor for the ARMAX model. And well, if you multiply by c, this is the expression that you get. So this is the expression of the one step ahead predictor that we have found. So what you can do now is juggle a little bit with this formula. So what we'll do is on both sides subtract cqy of t, okay, and we'll do this also minus cq y of t over here, okay, but this one over here will simplify with this one over here, so that we can write cq prediction minus measurement is bq ut minus aq yt, right? So what we do here is simply do minus 1, okay, so we have subtracted the prediction minus the measurement, so we have to add it again, and this is what we do, and then the other side remains the same. But if you have a look, this is the prediction error, the measurement y minus the one step ahead prediction. So what we have over here is minus epsilon minus the prediction error. Okay, so we can rewrite it as this formula. The minus is over there, so cq minus 1 times the prediction error plus the one step ahead prediction minus the measurement is equal, well, to the right side of the equation. It hasn't changed. So what you can do now is obtain the expression of the one step ahead predictor, right? And this is the formula that we get. So we have this one over here. The y we can put on the other side, so this explains this term over here, right? And we can take the other one to the other side as well. And we like this kind of formula because we have something acting on the U's and it involves only B's. We have something acting on Y, the output, and it only involves A's. And we have something acting on the prediction error and it's only, well, involving C parameters. By the way, you see that if CQ is equal to 1, this would be the case for an ARX model, well, this term would disappear and we obtain the predictor that we had obtained for the ARX model. So what we would like to do is to write this in a, well, neat way. And remember that we have already defined theta. It's composed of the A's, the B's, and then the C's. And to do that for the ARX model, we had defined the regressor vector phi. And it was composed of, well, because of this sign over here, minus yt minus 1 up to minus yt minus a. And then if we have a delay of nk, we had u of t minus nk up to u of t minus nk minus nb plus 1, right? So this is for the ARX model, but it will also be valid for the ARMAX model because this first part is in common, of course. And then we'll have to add something with the residuals, right? C is a monic, it starts with a 1 and then it's, well, C1Q minus 1 up to CNCQ minus NC. Okay, and the C's, you've got them over here. So what you'll have to do is add the prediction errors up to epsilon t minus nc, right, and transpose, because this is a column vector. Okay, and if you do things like this, what you will be able to do is to write phi of t transposed, that makes it a row vector, times theta, because it is a column vector. So let's have a look if what we had found previously is correct. So remember, this is the parameter vector, it's a column vector. You have the A's, the B's, and the C's. This is the new regression vector. It's also a column vector, and it's the same as for the ARX model, except that we have added the prediction errors from t minus 1 up to time t minus nc, and I think that I forgot to put the theta dependence previously. So we can write the predicted output as the transpose of this vector. This would be a row vector times theta, which is a column vector. And you see a major difference with respect to the ARX model is that now the regression vector is theta dependent. Okay, so you cannot write the one step ahead prediction as a linear function of the parameters because of this dependence, and this is why we call this a pseudo linear regression. But of course this pseudo has a huge impact. So why is there such a huge impact? Remember that we could write, well, the prediction at time 1, right? And again we'll have theta over here. This is a row vector, and what we want to do is to make sure that this corresponds to y1. You can do the same from y2 up to yn, right? So this is phi transpose in 2, again times theta, and then up to phi transpose n theta times theta. So we can write this as y is equal to phi, but phi is now a function of theta times theta. So what we want to do is find a theta, okay, that makes, well, this quantity here, y, it's a vector minus phi of theta as small as possible. But because of this dependence here in theta, this is no longer a least squares problem, right? So we have to, this would be then the optimal or the estimate, right? And here the minimization is done with respect to theta. So this is no longer a least squares problem, so we have to use optimization, right? If we use optimization, we use the ideas of the course of optimization of last year, and well, you run the risk of ending up in a local minimum. So the fact that we have added a little bit of flexibility in the noise model has had a huge impact when we talk about how we compute theta hat. We'll now apply k-step ahead prediction to ARMAX models, and the underlying k-step ahead prediction equation is this one: h bar k q and h tilde kq are related to this equation, okay? And this equation, well, the idea was that we had to kind of decompose in terms that are unknown at time t minus k and terms that are known at time t minus k. Here you find the expression of h bar kq, and here you find the expression of h tilde kq, right? So let us apply this in the case of ARMAX models. And in the case of ARMAX models, HQ is given by the transfer function CQ over AQ. So we'll decompose it at HK bar Q plus Q minus K H tilde KQ. H bar KQ, this is a sum, finite sum, so this is really a polynomial. Remember that h0 is 1, so this polynomial k over here is monic. Here h tilde kq, it's an infinite sum, so this is really a transfer function. Of course the denominator will be a and the numerator is unknown, we'll call it L. This looks a lot like what you've done in the course of model predictive control with my colleague Thomas Museur. So if you multiply by a and rewrite things, then you obtain this type of equation, which is called a Diophantine equation, and this is the type of equation that you've seen in the course of model predictive control, of course, but also in the course of digital control, right? So what we'll do now is plug in. So this is CQ over AQ, right? This will be KQ, and this will be BQ over AQ, and this will be LQ over AQ. What we can do is cancel out the A's and rewrite things. So the k-step ahead prediction is BQ KQ over CQ u of t, and the second term will be LQ over CQ y of t minus k. So this is a relief. Indeed, the expression is correct. Well, another way to obtain this k step ahead prediction is as follows. Remember that this is really the decomposition of CQ over AQ E of t, and this is H of Q over here. So this is coming from the decomposition CQ over AQ is equal to KQ, a polynomial, plus Q minus K LQ over AQ. And this was this Diophantine equation, right? So this is how we obtain an equivalent description of the system. This is the part that is not available at time t minus k, so our best approximation of that part is 0. So this is why the k step ahead prediction is only this part here and this part over here, right? So E can be reconstructed using U and Y. So let's write it over here. E of t minus k. This is 1 over the noise model. And then y t minus k minus GQ U of t minus k. Right? 1 over h, that's a over c, and here we have g over h, so that's minus b over c, right? So what you can do now is collect all terms in u. Okay, this is what you obtain over here. We put the b over c up front, and just to show you that this is from this equation here, this is simply kq, right? And so this is another way to obtain the k step ahead prediction, but in this way you do not have to know the k step ahead prediction formula of the previous slide. So this is the k step ahead prediction that we have found, and if you write this in terms of these impulse responses of these transfer function, you can really make it explicit in the sense that you write it as an infinite sum. If you multiply by c, you have the, well, implicit or recursive expression. So let us now have a look at the commands. This is again the part that is common to what we've seen previously. Remember that these are the commands to obtain an ARX model. So here for the ARMAX model, first an ARX model is identified, and then we use it to initialize things when we run the ARMAX command. Remember that here we'll have to do optimization, so initialization is really an issue. So what we do is take the ARX model, we add a C polynomial that is just the constant 1, and then we use this, well, ARX model to initialize the procedure when we do optimization. So this will result in an ARMAX model that you can, well, have a look at using the command present. An alternative command would be to just use ARMAX using the data and then use a vector with 4 elements, and A and B, and now this is NC and this is NK. Okay, so here you will lose the advantage of initializing the model with the ARX model in the iterative procedure. You know here that you have used NC is equal to 2 because you know that you have 2 coefficients over here, right? So since we have an iterative procedure and we run into the risk of having a local minimum, what you can do is reinitialize your model and start the estimation from another starting point, and this can be done using the command init. We had seen something similar for the command NLARX to identify a nonlinear ARX predictor, and this is to avoid being trapped in a local minimum. Before going to an ARMAX structure, you should always first identify an ARX model and then look if the ARMAX structure gives a substantial improvement. If not, we'll keep the simple ARX model. It has advantages because you do not run into local minima, and it's also a simpler model structure. Just for your information, there is a family that is called the generalized equation error model structure, and it has again a degree of flexibility in the noise model, so that GQ of theta is BQ over AQ, right? And HQ of theta is CQ over AQ dq. So you see that you have some additional degree of freedom, and you have the possibility to make the denominator polynomial of the noise model different than the denominator polynomial from the input-output transfer function. So far we have considered model structures where the polynomial AQ is in common for G of Q, the input-output transfer function, and H of Q, the noise model. Well, imagine that you have now a system with a noise model that is complex, and that you try to use a model structure with the noise model is a simple noise model, so it's not really capable of representing the actual noise model. Well, then you'll have a mismatch in H, the model, the noise model. But since A is in common with G, well, this mismatch in H will also cause a mismatch in G, even if your G is capable of representing the real G. So this is why we now consider model structures where G and H are modeled independently. Well, the first such model structure is the output error model structure, where this is the input-output transfer function G of Q, and H of Q is simply equal to 1. Okay, this is why we call this an output error model structure, because the error, the white noise sequence, is added at the output. Okay, so the B polynomial is exactly as previously. Okay, so remember that we can have a delay nk, and here we'll use another polynomial f to distinguish with A, because when we use A we have this polynomial in common between G and H. Here this f only appears in the transfer function G, the input-output transfer function, but apart from that f takes the same form. It's also a monic polynomial, and it is of degree nf, right? So the parameters are again stacked in a column vector. We follow the alphabetical order, so we put first the B parameters and then we put the F parameters. So this is a representation of how Y is generated. Okay, U goes through the transfer function, and at the output we add noise. For the ARX model structure we had something a bit different. We had, I'll put it like this, BQ, right? Then we have e of t that is added, and at the output we have 1 over a q, and this is producing y of t. This is the input. Okay, so to obtain an ARX model structure, well, you take the 1 over f and you put it over here, and since it's now common to G and H, you would have to call it A, and then you obtain the ARX. So really the difference lies in the fact that here the autoregressive part is at the output and here it's at the input. So this is the data generation mechanism for an output error model. So in equation it's BQ over FQ UT plus E of T. If you want to write the one step ahead prediction, you have to look at the part that is not predictable at time t, and we have just this part over here, and you replace it by, well, the expected value, which is 0. So the one step ahead predictor is obtained by this equation. So the one step ahead prediction is really the simulated output, right? So there is no difference for an output error model structure between predictor and simulator. So predictor is equal to simulator, and this means that since we are doing prediction error identification, we are trying to minimize the prediction error. In this case, if you use an output error model structure, we are also doing simulator error identification. So we are trying to make the simulation error as small as possible. This is why these output error model structures are really good in simulation, right? Well, this predictor, you can also obtain it, if you wonder, by the formula of the one step ahead prediction, and this is h minus 1q gq working on u of t plus 1 minus h minus 1q applied to y of t. Okay, and obviously h of q for an output error model is equal to 1, so this term disappears and this one disappears, and this is indeed here gq, right? So this is the predictor and also the simulator. So as before, we would like to write the one step ahead prediction in such a nice fashion, where we have here the parameters stacked in theta, and here we have some regression vector. So let's have a look at this, and if you write it like this, and I'll put f of q in front. So here f is 1 plus f1q minus 1 up to f and f q minus nf. So you can write this one step ahead prediction as, so multiply by fq, so this multiplied by 1 gives this one, and then this one multiplied by this one, and taking it to the other side we have minus f1, and we have the prediction at the previous time instant. Okay, and then we have lots of terms, and then we have the last one here, minus f and f, and then the prediction at time t minus nf, right? And obviously plus b1 u of t minus nk, okay, because we are considering a general delay of nk up to bnb u of t minus nk minus nb plus 1. If nk is equal to 1, this is simply u of t minus nb. So what you see here, indeed, we can write it like this. And what do we have to put in the regressive vector? U t minus nk up to u t minus nk minus nb plus 1. This is because we take theta as first the b's and then the f's. Okay, so this is why we have this order in the regressive vector, and then we put here these values over here with a minus sign in the regressive vector. So here in the regressive vector what we have is the previous one step ahead predictions, okay, and obviously they depend on theta over here. Okay, so again we have this dependence of the predictor on theta, the parameters, but also in the regression vector. So we do not have a nice formula that is linear in theta because of this dependence, right? This means that again we cannot use least squares and that we have a pseudo linear regression. Okay, and this means that we'll have to use optimization to obtain theta hat. So again we can have a look at the commands in Matlab Simulink. Again, this first part should look familiar by now. So this is the output error command. So this is what you have to run to obtain a output error model, but I'm showing you here that you can use options because we're doing, well, an iterative search. Okay, so you can display what is going on in the optimization procedure, and you can set parameters such as, for instance, the number of iterations or the tolerance in the stopping criterion and things like that. This makes the link with the course of optimization of last year, and these options will they appear over here. So n here is nb, and this is nf, and again this is nk, the delay. So the order is different. Okay, nb appears first, so this is the numerator polynomial and this is the denominator polynomial. And as usual, you can have a look at the parameters, and you should, and have a look at, well, the values of the parameters, but also their confidence interval. So what you can then do next is, since you're again in an iterative procedure, is look what happens if you start the iterative procedure from another starting point, and you can achieve this using the command init. And again, this is this trick to avoid being trapped in local minima. Well, as shown in the previous slide, you can actually see what is going on, if you want to, during the output error model identification. And you can see here that also using an output error model, we initialize the model using an ARX model. You can see the iterations here and how the cost evolves. You can see the step size and etc., and you can see what the cost is and what is the stopping criterion. So remember that the predictor is, one step ahead predictor is, well, BQ over FQ, and remember that FQ is 1 plus F1Q minus 1 plus up to FNF Q minus NF. Okay, so you can write y hat as minus f1, y hat t minus 1, etc., right, up to minus f and f, y hat t minus nf, and then you add, of course, this part over here, and I'll call it simply bq u of t. So bq u of t, you can see it over here, and this part over here, this corresponds to the part that you see over here. So this is looking a lot like what we had for the ARX predictor, with a major difference is that what was entering this chain over here was not the previous simulation but the actual output. Okay, so this is really important to see, and have a look at the ARX predictor to see the difference. So what we can do is replace this linear combination of previous inputs and previous predicted values. Well, we can replace it by a non-linear function. So for instance, a neural net that will act on previous inputs and previous predicted outputs. The remarks that we made about, well, having the non-linearity only at the input or only at the output are also valid for this non-linear output predictor. Okay, but to obtain such a model, you have to do identification, and you have to realize that identifying this type of non-linear predictor is harder than to identify a non-linear ARX model or predictor, because here what is entering the neural net are previous predicted outputs, whereas in the non-linear ARX they are, well, previous measurements from the system. Well, the next member in the family is the so-called generalized output error model, or the Box-Jenkins model. And as you can see here, G, the input-output transfer function, and the noise model are independently parameterized. So the parameters that appear in G and the parameters that appear in H are different. Okay, so here you can write theta as theta 1, theta 2, and theta 1 will only parameterize the input-output transfer function, and theta 2 will only parameterize the noise model. Okay, so they give good results in prediction and also in simulation. The one step ahead predictor is given over here. I'll leave you the calculation as an exercise. Well, you can of course use that type of models, but you have to realize that of course this will again be an iterative search, right? And well, the complexity of the model will be greater if you have to implement a predictor based on this type of model structure. It will of course be much more complicated than the predictor associated, for instance, to an ARX model. This is why in practice we have often the tendency for prediction to simply stick to ARX models. You will see that they work very well, for instance, for flood prediction. Just for your information, the most general model structure is given here, and when you compare it with the Box-Jenkins model structure, you have the appearance of an A polynomial, so that you have parameters in this polynomial, the A parameters that are common to G and H. But this is just for your information, because this type of PEM models, there is a PEM command in Matlab, are not used very often. Well, a time series is a series of data points with only outputs. There are no measured inputs. There are inputs, of course, to the system, but these are not measured because they are not available for measurement. Examples are, for instance, series of ocean tides, count of sunspots, and, for instance, the value of your favorite share, right? So you can apply the course to predict the price of the share for tomorrow and become very rich. The fact that I'm still working at ICAM probably means that I've not been very successful, but it could also mean that I'm rich but simply very motivated. So for a time series, well, it is assumed that the output of the system is modeled as white noise that goes through some model h of q, and well, depending on h of q, you will give those particular models a name. So if h of q is 1 over aq, then we speak of an AR model, and if h of q is cq over aq, then we speak of an ARMA model, and this is a model that we've encountered previously in the course and that we've used to illustrate some concepts. If there is an integrator in the system, then we speak of an ARIMA model. So as mentioned before, this is HQ is 1 over AQ, and the underlying relation is this one. And if you want to identify such a model structure based on data, well, there is a special command AR. You can do the same for the ARMA model. So HQ here is CQ over AQ, right? And the underlying equation is therefore this one. You see that, of course, when CQ is 1, this becomes an AR model structure. Well, this type of model structure you can identify given data using this command over here. Okay, so you have to use the standard ARMAX command, just put an output, and if you only put 2 parameters in here, it will be smart enough to know that this is NA and this is NC. So if you want to predict the price of a share, well, you have to get a collection of data, use, for instance, an AR model or an ARMAX model, identify the model based on the data, and then write the predictor. I haven't told you before, but of course the formula of the one step ahead predictor is still valid, and since there is no exogenous input, it just simplifies to 1 minus h minus 1 q applied on y of t, right? And this construction of the predicted value can be done, as you will see in the system identification lab, using the function compare. So we can also identify finite impulse response model. Then G of Q can be written like this, and over here we have the impulse response, right? And here we have only n elements in the impulse response, and we have seen that, well, this FIR model is a special case of the ARX with NA is equal to 0. Okay, so identifying a FIR model is, well, a linear regression. We have seen that this is the case for identifying an ARX model. It's also a particular or a special case of the output error system with HQ is equal to 1. Okay, and since in this case, well, G and H are independently parameterized, it will give you a model that is robust to noise and is also good in simulation. Well, it cannot all be advantages. Well, the disadvantage of using an FIR model is that, well, they require a lot of parameters. You have to identify every parameter in the impulse response. So assume that we have a first order type system, then the impulse response is alpha to the power t. Okay, so this is something that is going down, at least if it's more than 1. Okay, but if of course is alpha in modulus is smaller than 1 but close to 1, this will go down very closely. We have here an impulse response that is parameterized, that can be parameterized using just one parameter, but if you use the FIR model structure, it will use many parameters. So FIR models are identified either using an ARX structure with NA is equal to 0, an output error structure with NF is equal to 0, but the easiest is to use the command impulse est, and we have used it in the air dryer example at the beginning of the course. I think that's what CRA is correlation analysis. This is a somewhat obsolete command that is used in older versions of the system identification toolbox. So do not forget that you can also parameterize your linear system in terms of a continuous time transfer function, and then you know that an obvious model structure is the Broida model. So you have one time constant t, a gain and a delay. This type of model, as you know, is used very often in industrial applications. So what you can do is use Matlab's command tfest, and in the slides that follow there's an example for that, but I will skip it in this video course. The slides are there for your information, but don't forget that you can also obtain the model using the command fmin search, and this is what you've done in the lab that is associated to fundamentals of control theory.